In the world of bioscience, we've gone way past just sequencing genes. We're now in the age of data mining, where the real breakthroughs come from sifting through these enormous mountains of existing genetic information. But the sheer scale of all this data is creating a bottleneck, a huge problem you might not expect.
Just look at this number for a second, 15 petabytes. And get this, that's not the total data in the world, that's the storage capacity of a single modern platform built just for life sciences. It's an amount of data that's kind of hard to even wrap your head around. So what does that actually mean?
Well, to try and put it in perspective, one single petabyte is like storing the text from 15 billion books. And the platforms we're talking about can hold 15 times that. See, we're not just collecting data anymore. We're using these massive digital libraries to model diseases, to predict how drugs will work, and to unlock the fundamental secrets of biology. And to do that, you need an absolutely immense amount of computing power.
Okay, so this is where we hit the big problem. You can have the fastest, most powerful computers on the planet, but if they can't talk to each other and to all that data quickly and efficiently, you just end up with a massive scientific traffic jam.
Think about a modern research setup like a super high-tech logistics operation. You've got these incredible factories, right? Those are your super fast servers, each with dozens of processing cores. Then you have these gigantic warehouses, the storage systems holding all those petabytes of data. And on top of that, you have the brilliant software, the assembly line, that's designed to make these amazing discoveries. Everything seems to be in place.
So you've got all these incredible pieces, right? The powerhouse servers, the vast stores of data, the really smart applications. So what on earth could be the weak link in this chain?
It's the network, the very thing that's supposed to connect everything together. It's like trying to connect your super factories and your mega warehouses with a tiny single-lane country road. That's basically what a traditional 1 gigabit per second network is to a modern research cluster. Those multi-core servers can chew through data so fast they completely clog up that old connection, and groundbreaking research just grinds to a halt.
Okay, so how do we fix this massive traffic jam? Well, to do it, a modern scientific network has to meet a very specific and very demanding set of requirements. It's not just about raw speed. It's about being smart, scalable, and incredibly reliable. And this checklist is pretty intense. The network has to seamlessly connect hundreds of servers to each other and to that massive data storage. It needs both high throughput for moving gigantic files and super low latency, meaning almost zero delay. On top of that, it has to be able to grow as you add more servers, it has to be on 24/7, and it needs to be open so researchers can customize it. It's a really tough list of demands to meet. So how do you actually build a network that can handle all of that? Well, you don't just add a lane to the old country road. Nope. You have to build a brand new, multi-lane data superhighway using some really incredible technology. The first thing you do, a massive upgrade. Moving to 10 gigabit Ethernet gives you 10 times the bandwidth, but it only costs about twice as much. That's a huge 5x leap in value. But the really mind-blowing change is latency. We're not just getting a bit faster, we're jumping from delays measured in milliseconds all the way down to nanoseconds. That's not just a little faster, that's 1,000 times faster. We're talking delays measured in billionths of a second.
So, how on earth do you get that fast? Well, one of the key technologies is something called cut-through switching. Basically, instead of waiting for an entire chunk of data to arrive before sending it on its way, the switch just reads the address and forwards it almost instantly.
Going back to our logistics analogy, this is like a package arriving at a sorting center, but instead of ever stopping, it's scanned midair and immediately redirected to the correct truck. There's no stopping, no waiting, just pure uninterrupted speed.
All right, the next piece of this high-speed puzzle is even cleverer. It's a technique called kernel bypass. And this isn't just about the network path. It's about making the server at the end of that path work a whole lot smarter.
So what does kernel bypass actually do? Well, it basically creates an express lane for all that data. Instead of data arriving and having to be processed by the server's central traffic controller, the CPU, it goes directly from the network right into the application's memory. This offloads all that traffic management work, which frees up the server's brain power to focus on what it's really supposed to be doing, running the complex science.
Okay, I know what you're thinking. Nanoseconds, kernel bypass. This all sounds super technical and abstract, right? But believe me, these tiny fractions of a second add up, and their impact on real-world research is absolutely profound.
And here it is. This is the real payoff. With those old network bottlenecks, a complex research job could literally take years to finish. But as you can see here, with these new networks, that wait time just plummets. We are talking about slashing research times from years down to months or weeks, or in some cases, even hours. I mean, that is a complete game changer for the pace of science.
And you know, it's not just about pure science. There are massive commercial reasons driving all of this. In the private sector, especially with drug development, speed is absolutely everything. Being the first to discover something or bring a new drug to market can determine the success of a company for a decade. The pressure is just immense. So, let's bring it all home. Why does any of this matter? Because a modern network isn't just some IT upgrade. It's literally an accelerator for science. It means faster gene analysis. It means we can model biological systems in ways we never could before. It means we're accelerating the path to discovering new drugs. And in the end, it provides a critical competitive edge in an industry where every single second counts.
So these incredible new networks are the superhighways that finally broke today's massive data traffic jam. But in science, the data never stops growing. It's always expanding, always doubling. So the big question we're left with is, what kind of highway will we need to build for the data deluge of tomorrow?